Hi, everybody, and thanks for coming to the session. And thanks to the translators, technical team, and all the staff here. As the MC already mentioned, I will be talking about composifying your not compose code. Composifying is not I guess, a verb in the English dictionary, but here I'll be talking about, making code that is not compose, is not written in compose, available for the Compose API. And I will be showcasing the Android Maps Compose case study. The Android Maps Compose is a library from Google that has been built at the top of Google Maps, which is a library that doesn't support Compose, and creates this Compose API interface for us. Very briefly about me, I'm CTO at Snap Mobile. We are a small software company in Munich, in Germany. I'm originally from Spain, so as you might have guessed because of my accent. I've been for about 20 years in tech, and I'm mostly working on the mobile part, Android and iOS, but I also try to do some data science and AI, so that means Kotlin for data, TensorFlow, and Python. I'm also the maintainer of the Kotlin Weekly. If you don't know about it, it's a newsletter similar to Android Weekly that I send on Sundays, containing some news about the Kotlin world, new libraries, new releases, etc. So check it out, and maybe you subscribe. And I wrote a few books in the past, which are very outdated by now, but in case you're interested. Let's talk a bit about the world before Compose. For over a decade, the Android UI development was dominated by an imperative XML-based system. Similar to how Swing was working on Java, we have a separation between the UI and the logic that governs this UI. We build UIs using the XML layout files and manage their state programmatically in activities and fragments. This approach was powerful, but often led to complex state management and boilerplate code, especially boilerplate code. If you've been using the view system, this led to functions to locate the XML file, like find view by ID. There was a few libraries that improved the process a little bit, but generally we ended up with a lot of code just to deal with the XML files. This is an example that will probably be familiar to you. We have a frame layout that is hosting a map view, and where we set a few attributes like layout width or height and the ID. This is an example of how the map view from Google could actually be added to an XML, and then later we added on our Java or Kotlin files some code that could bring this map view and start changing its attributes or performing certain operations. Now, since a few years, we have the rise of Jetpack Compose. Jetpack Compose is a modern toolkit designed to simplify the UI development. This is a general trend in the industry, not only on Android, but we see on Swift UI, on iOS, Flutter as well. The industry seems to be moving in this direction. This embraces a declarative paradigm. So instead of telling the UI how to change by calling a function to set the state, we simply describe how it should look like for a given state. This shift to a state-driven UI simplifies development and reduces bugs, at least in theory. In practice, if we don't do it correctly, it's also dangerous, but that's a topic for maybe another presentation. This is a hello world in Jetpack Compose. We can see that we have our composable annotation, and then our function called greeting receives a string and adds it to a text field. Very simple, nothing fancy. Now, we have an interoperability challenge. Most Android apps are not greenfield projects. They have a history and a code base built with the traditional view system. Sometimes we might have it combined. Part of the application is written with the view system, part of it, the new components maybe with Compose, and they need to interact with each other. Sometimes we need to use mature and well-supported libraries like the Google Maps SDK that were not designed for Compose. The Google Maps SDK, as well as other libraries, is just created with the view system in mind. So the problem now is, how do we smoothly integrate the map view, a traditional Android view, into a Compose UI tree, which doesn't accept views in principle? Well, the most important actor is the Android view, which acts as a bridge between two worlds. This is the official interoperability solution from the Compose team. It acts as a container for an old-school Android view, and this Android view composable is built to manage the view lifecycle, layout, and state within a Compose function. How it works. The Android view composable takes a factory lambda to create the view and an update lambda to reconfigure it anytime there is a recomposition. We have another lambdas like on reset and release that we'll see later as well. The factory lambda, it's called once to create the view instance, and it's a key part of managing resource-heavy views. The update lambda, it's called on every recomposition. This is where you pass the state from Compose into the view. Here we see a hello world with Android view. This is a very simple one. You see that we also have the composable annotation, and inside our view, my custom view in Compose, we call Android view. On the factory method, we have access to the context as a parameter, and we call the constructor of our view, passing the context. On the update lambda, we receive the view as a parameter, and this is what we are going to call on every recomposition. We'll take our view, call the method setText, and update it with the string myState that we have received here. Of course, this is a very simple example. It will get more complex for complex views like the Android Google Maps. Oops. Why not just Android view? This is a simple text view, and the Android view approach is sufficient. But map view has its own complex lifecycle requirements. If you have worked with Android maps, you know that you need to notify of the host lifecycle events. So we need to call the map view on create, map view on resume, etc. to initialize it properly and manage the resources. Just grabbing it in an Android view is not going to work because the Android view doesn't automatically call these methods. Now, let's take a deeper look at the map view. Map view class requires its parent activity or fragment to explicitly forward these lifecycle events. If you don't do this, the map is going to fail to load, or it might crash the app, or you might end up with memory leaks. This is what I mean here. We have this onCreate method, where this is the method from the activity, or it could be the method from the fragment. We called inside onCreate the super onCreate method, and right underneath we call the mapView.onCreate. We do the same for the onResume and for all the other lifecycle methods. This doesn't happen automatically when using the Android view bridge. So we have a conundrum or a problem here with the lifecycle. How do we get the parent composable lifecycle information? A composable itself doesn't have a direct lifecycle like a fragment. If you've been using composables, there is no way or no easy way to deal with the lifecycle. The solution: we need to find a way to observe the lifecycle of the composable host, the activity, or fragment. One potential solution is to use disposable effect. The disposable effect is a composable function that creates an effect that is tied to the composable lifecycle. The code inside disposable effect runs when the composable enters inside the composition. We have an onDispose block that runs when the composable is leaving the composition. This is crucial for a cleanup step. If we want to shut down a view or set it to null, etc. Now, we need to actually access the lifecycle. So Compose provides us a composition local called local lifecycle owner. This lets us access the lifecycle owner of the containing activity or fragment from any composable in the tree. A very simple line. This is something that we could use inside our composable. We just called local lifecycle owner.current.lifecycle, and bam, we have access to it. Let's connect the dots. Now, we want to composify our map view. That means that the map view must be carefully managed with a lifecycle event observer. This observer should only be active when the map view is actually attached to a window, not before it gets attached and not when it's not attached. We are going to use the Android view factory and on-release callbacks to create and clean up the map view and the associated observer. The map lifecycle event observer, it's a state machine that makes sure that the map view calls are made in the correct unexpected sequence. Let's take a look at the current code. This is actually the code from the Android Maps Compose library, the one that you can see in the repository. Here, we can see that inside the factory method, we receive the context as a parameter, and we call the constructor for map view. We need to pass the context as a fair parameter, and then we have a Google Maps auctions factory that initializes a few relevant attributes for the map. This returns us the map view, and we'll keep working. Map view requires component, or you can use a component callback to determine what happens when the configuration changes or when the device is on low memory. In this case, you can see that for the on low memory case, there is one that is deprecated in the component callback itself. We still add it here and mark it as deprecated, and essentially inside on low memory and on trip memory, we trigger the on low memory method from the map view to connect it with this callback. And here we are going to create a map lifecycle event observer passing the map view as a parameter. Now, more on the factory method. This line from here, it's going to create a map tag data for the map view to identify it univocally. This is something that we can do to provide an identity to our map. Now, we also have the unattached state change listener, which is crucial to determine if the map has been attached to the window or not. We override these two methods. First one is the onViewAttached to window, where we find inside the view tree of the lifecycle owner the lifecycle and just add an observer. Similar one on the onViewDetached from window, but in this case, what we want to do is the map view is not attached to the window anymore. So we are going to remove the observer. We are going to set the lifecycle as null, and we are going to move to the base state. Let's see what is this base state and which other states we have. And we have this couple of methods here that I'll also showcase. As mentioned, we have the onRelease method. This is being called for shutting down the map. So we can see that we set the tag as null. We move the lifecycle observer to the destroyed state. And we have the update method. This method gets called on a recomposition. So we need to make sure that the map updates its components to reflect changes on listeners or the current content or whatever. Okay, here, this is the launch subcomposition method that we have on, we're calling from update. We see that we're launching coroutine here. And the most relevant part is that here we call the await map function to bring the map. And apply the, create this composition using a map applier, specifying the parent composition, and we try to set the content via this composition. Finally, we just dispose it. This is what happens on the update method. Now, the lifecycle state machine. The map lifecycle event observer is not just a simple when statement. It maintains its own current lifecycle state to ensure that the map view methods are invoked in the valid order. It handles transitions both up, on create, on start, and down, on pause, on stop. This is a more robust pattern that prevents incorrect state transitions and potential crashes. Let's see how this part works. This is the map lifecycle event observer that we've seen before. The default value for the current lifecycle state is going to be just initialized, and we'll have a few methods to help us transition through this state machine. First is, what do we do when the state changes? Note that this is a method being overridden from the lifecycle event observer. If the event is on destroy, we are going to move to the base state. And if not, we're going to move to the lifecycle state. See that here we are calling the event.target state, the state that we're targeting. Move to base state is simple. If the current lifecycle state is bigger than lifecycle state created, we just move into lifecycle state created. This is, by the way, this state.created is an enumeration that we can access if we open this class. Move to the straight state is also simple. If the current lifecycle state is bigger in this enumeration than the initialize, we will move the lifecycle state to destroyed. And move lifecycle state, also a simple one. If the current lifecycle state is different than the target state, depending on whether it's bigger or smaller, we just move up or move down. Move down just calls the lifecycle event .down from, specifying the current lifecycle state. It creates an error in case there is no event down from to provide some security for the map, and invokes an event, this function in the next slide. And move up, analogously, does the same, but calling the function up from. Invoke event is the function that manages these equivalences between life cycles. You can see that we compare, and if the current state of the life cycle is onCreate, we'll just call the mapView.onCreate function, passing a bundle. If it's on start, mapView on start, and so on for every mapView lifecycle method. And last but not least, we update our current lifecycle state. You can see that this class is the glue between life cycles, the one of Compose and the one of our view. The map view now is safe. We have now successfully integrated a map view into a composable. The map is initialized, is managed, and is cleaned up correctly, preventing memory leaks and crashes. However, this is just the first step, because the API is still too low level for a good developer experience. If you are a developer, remember, developer that was using the view system would call functions like set text, change color, etc. But on Compose, we don't call those functions. We need to provide them via an API. So we need to create an API to expose the internal APIs from Google Maps. An idiomatic Compose API must be declarative and state-driven. The users of our library shouldn't have to think about maps views or lifecycles or bundles, because those are not part of the Compose world. Our job is to create a clean and an elegant facade on top of a complex implementation. There are also some Compose API guidelines. If you don't know them, I encourage you to search them. You just can go to Google and search something like Compose API guidelines that describe how a Compose API should look like. They define things like you should always have an initial modifier parameter with a default value and a few other examples. So that's also important to create an API. So as we mentioned, on the imperative, the old way, we would call a method to change the UI. In the case of maps, we could do map.animateCamera with a new position. And in the declarative, the new way, we change a state object, and the UI is going to react. For example, we will pass to our Google Map composable a camera position state, and when this changes, we update the composable. This is the core design philosophy of Compose, and we must follow it. For example, let's take a look at the camera position state class. The camera position state is a custom class that holds the current camera position, zoom, and some other properties. You could think of it as a state holder that can be observed for changes. Very basic example on Android Maps Compose. We can define our camera position state using this remember camera position state function. Inside, we will set the position as, and this is part of the Google Maps library, from the lat long zoom, specifying Singapore. This is a location that we have, and 11F as the zoom. Please note that I'm using this remember. The remember pattern is very important in Compose. What's the implementation, how the implementation of this remember camera position state looks like? I have to say here something. I was talking with the translators before. I sent my slides the 1st of September, and this was the content I sent. But on the 5th of September, we changed something on the library that I will explain now. You can see that this remember camera position state receives a key to univocally identify the key for this remember. And then we have this cross inline init here that it's passed to the remember savable. This is a compose function. So you can see that the remember savable receives the key. Then we need to pass a saver. And then inside, we initialize our camera position state. Now, Google actually released on one of the Compose versions. That was actually by April 30th, but we had to change it a couple of weeks or last week for a bug report. They actually deprecated the remember savable with the custom key parameter. That means this one from here. So right now, we submitted a pull request that you can see here on the Google Maps repository, deprecate remember camera position state, and this is the code that we have. We have essentially rendered as deprecated the function that I just showcased, and we have created a new one that is exactly the same, but it doesn't contain this key parameter, just so you are aware of the change here. On this page from the Google repository. They're claiming that there was a potential bug when using remember shapeable with the key. So that's on the presentation, but it's not the way you should be doing things right now. You should use the function that doesn't contain the key. Well, coming back to moving forward with the camera position state class. The camera position state is a class from the Maps Compose framework. It contains a few parameters, such as is moving, which determines if the camera is currently moving or not, including any kind of movement. If we're zooming, if we're rotating, if we're panning on the map. Then we also have another variable to determine the reason for the camera to be moving. This is something that we use also to mirror the underlying framework. We try to make Android Maps Compose as reflective of the underlying SDK, and part of it is providing support for those methods. Let's keep looking at this class. So something relevant, this is still part of the camera position state. Something relevant here is that you can see we are using Google Map. This is the actual Google class. And we have a couple of things here. We're using this lock here to make sure that the access to the map has been synchronized to avoid, undesired effects and provide threat safety. So the map is not being accessed multiple times and, leading to problems that you know as developers. Now, we have this internal set map function that what does is also using the synchronized lock, it makes a few checks. It checks if the map is null and the map that we're passing as a parameter is null, then we just return. If both are different of null, that means that the camera position state can only be associated with one Google map at a time, so we return an error. And we only move forward if, in case the map is different of null, we just set this is mapping as false. Otherwise, we just move the camera to the position that we have specified. And we use this on map change listener here to notify that the map has changed its status. This is a one-way data flow. The developer changes the camera position state from the upper side, you could say. Then the Google Map composable detects this change, and the library internal logic then calls the move camera method on the underlying map view. We need also to manage user interactions. When the user drags the map, the underlying map view is going to fire a callback. The library code is going to be listening to this callback, and then it will update the camera position state to reflect the new position. Now, we need to handle events and callbacks. If you've been using with views, and more specifically the Android Maps views, we use often listeners like set-on-map-click listener to specify what happens when the user clicks on the map or moves the map or process to an interaction. But the Compose API doesn't use setters. Instead, it uses lambdas that are passed as a parameter to the composable. That's the Compose way of dealing with interactions. This is a very simple hello world using these lambdas. So you can see that in this example, we have our Google Map composable. We have also an on-map click listener. This on-map click listener has access to a lat long, the one that the user has clicked. And in this case, we just print into the screen that the map was clicked in this lat long. And we can add, for example, when there is an on-map long click, we can add markers, or we can proceed with our custom implementation for maps. I know this screen is very large, but bear with me. This is the interface for our Google Map composable, if you want to integrate it in your Compose app. Note that the first attribute is going to be a modifier. This is part of the Compose API guidelines. First attribute should always be a modifier with a default value. Then we can observe that we have the listeners here, the listeners that provide the option of interacting with maps. Another comment to note here is that we try to keep everything exactly the same as the underlying SDK for, well, to keep aligned the functionality, correct? So note that the map click has exactly the same lambda as the set of map click listeners. So in this case, we start with a lat long and return nothing, etc. Same for all the other listeners. So on map long click also contains a lat long in the lambda, etc., etc. By default, they're set to null. That means no listener. And last but not least, we have content lambda, where we can pass more content to be integrated into the Google Map. We'll see later how we can use this for example, adding a marker, or adding a polyline, or adding another component. And maybe also interesting here, we have the properties that, of course, in the previous map were being programmatically set. We could call map.setMyProperties. Here, we just pass them as another attribute. Well, you can see that inside our map, our Google Map function, we are again using this remember pattern. We set our internal patterns, our internal listeners to the one that the user is providing, and by using the remember function, we make sure that this recomposes on any update to reflect the latest status. Now, we can add markers also declaratively. We don't want to call this set marker function or add marker function that was available on the view-based system, but instead passing it as the content lambda. This is very similar when you're using columns or rows on Compose. You do the same thing. Inside the column or inside the row, you have a content lambda that you fill with the content that you need. This allows you to add the marker and other maps objects declaratively. So again, a basic sample. Here we have our Google Map, and you can see that the marker is just simply added. We have a marker state. This is similar to the camera position state, where we can specify the position, and a list of all the markers. For example, here we could take a list of markers, and for each of them, we add an individual marker specifying the position from this place. Looks how simple it is. Just with a few lines, we literally have a Google Map with many markers. I want to show on Android Studio just the marker implementation was a little bit larger, so just so you see how it looks like. It's again composable. Note that in this case, we don't have the modifier parameter as the first one. The reason is that the marker can be modified through a modifier. The only way to do it is via another attributes that are not part of the modifier from Compose. But we pass the marker state. We see also that we have the same listeners here that we had for the Google Maps, and then a few attributes that are relevant for markers, such as draggable, flat, the icon with the bitmap descriptor, etc. Then what we are going to use it to add it is we're going to get our map applier. This is a standard Compose applier that has a few other attributes to deal with the map, such as the Google Map, the map view, and the map listeners. If you have been working with Google Map on the view system, you know that you need the map view and the Google Map to create it. So the beauty of this is that it's hidden externally to the user. They don't need to deal with all these classes. Note that here on this Compose node, we are also using a factory method and an update method, as we were using on Google Maps. And on the factory method, we call our applier, we get the map, and then we call the add marker function. So this is the view way of doing things, but we are exposing it through a compose interface. So the user doesn't need to care about the internal details of this implementation. On the update method, we just call an update function, specifying that we're going to add this value to the marker click or on window click or whatever we want to change. So back to the slides. The remember function is not just for creating map views. It's essential for creating and retaining the state holders like camera position state. This makes sure that the state survives recompositions and remains a single source of truth. This is a look at the final API. We have our Google map. We can pass our modifier. We can insert a marker with a given title and state. We have hidden all the map complexity and exposed everything via compose. Here is there is a short checklist for composifying libraries. We need to identify the view. What's the target? Is it a web view? Is it a custom chart? What are the custom methods from this view that we need to override? Every view is going to be different. We need to assess lifecycle needs. This is important to prevent bugs and crashes and memory leaks. Using lifecycle observer, we can mind the gap between the compose and the view. We can bridge with Android view. This is going to host the view in a composable. We need to manage a state. Remember is our friend, and we have state holders that we can use to manage the view state. And we need to design a declarative API. We need to hide from the user the imperative implementation and expose it via the declarative compose API. Some considerations. Performance. Android view can be a performance bottleneck if it's not used correctly. We have, in fact, some performance troubles with Android Compose, especially when we're using the clustering with many markers, and the performance is notably worse than the standard view system, especially when using thousands of markers. So minimize recompositions as much as you can. Make sure that all the user interactions are captured and correctly update the state. This generally means that for the target view, you need to go and see, in the case of Google Maps, for example, okay, what can I do? I have map on click listener, long click, etc. You need to provide or capture all those interactions. And remember that you'll have to test the underlying view separately from the composable. They're two separate items, you could say. And performance, which could be an interesting topic. It's not without cost to talk between compose and view system. You always need to take a decision on whether performance is going to have an impact, how important it is to you, and the architectural cost of interacting between compose and view all the time. An Android view is heavyweight composable. Placing it on your UI can introduce a performance overhead, and recomposition is expensive when it causes the underlying Android view to be recreated or reconfigured frequently. This is a generally good advice for compose developers. Be mindful of recomposition. And be also mindful of the overhead of creating complex view hierarchies, especially inside a lazy column or a lazy row. We actually have, on the Android Maps Compose repository, a sample using the lazy column and lazy rows, also for us to observe how the performance works there. And optimize for Android view performance. Generally, minimize recomposition. Only pass the necessary state to the Android view update block. Use remember as much as you can, or where it makes sense, but as much as you can. You need to cache expensive objects to prevent recreation on every recomposition. This is, for example, why we use it for map view and camera position state. Avoid Android view in a lazy column or lazy row. It can cause significant performance issues as the items are being scrolled on and off the screen. And measure and profile. You need to use tools like the layout inspector and the profiler to identify performance bottlenecks. Just a final thought, we don't have to choose between a modern UI toolkit and a mature ecosystem of libraries. Interoperability is possible and allows us to use both, building on the best parts of each world. Those techniques we've seen, I think, are a powerful way to bring a legacy Android code base into the modern Compose era. So I'm finished here. I just want to show one more thing, and well, is the repository, if you want to take a look. You can search for Android Maps Compose on Google, and you'll be able to access it. You have a full documentation on how to do everything, drawing on the map, polylines, advanced markers, how to create shapes, for example. So feel free to take a look. You have the entire documentation here if you want to see all the architectural details. And check on the issues. We are working on bringing it to support Compose multi-platform. It's still taking some time, but we'll eventually get there before the end of the year. So, arigato gozaimasu. Thank you very much. And happy to have seen you all here.